this and post it. All right, so fluids. So questions you should ask yourself, and this is sort of my philosophy on how I like to teach and how I like to learn. Most importantly, what is a fluid? So, you know, what is your definition of a fluid? What is the actual definition, you know, scientifically? You know, think of it this way, like, you know, I often, if someone asked you 2 hours from now or 3 hours ago, what is a fluid? How would you have answered it? And then how you would have answered it, how does that differ from, say, if you go to Google and ask Wikipedia what a fluid is, or you go to a scientific definition and ask what a fluid is? Then there's also this thing we have, our intuitive definition of a fluid, like what we think a fluid should be. So what you'll find is if you sort of source out for the definition, you might actually find different definitions of what a fluid is. So that means we in this class, or we in the physics community, or us in the scientific community, we all have to agree on what we think a fluid is. And so what we're going to take as the definition in this class is the following. So it's any material slash, I like to use the word substance, that can flow. Now, of course, your rebuttal can be, what does flow mean? Right? You could say, what does flow mean? Another way I like to think about a fluid, and this is, I think this is how your textbook likes to describe it. In any container, it takes the shapes container, or the shape of. So, I mean, it sounds really, really stupid, but if I had a cup and I put a rock in my cup, it still looks like the rock that I put in the cup. But if I have one cup with water in it, and then I take that cup and dump it into another cup that maybe is a different size, my water conforms to the new size, or it takes the shape of my new cup. So one of the interesting sort of thought experiments with that is, okay, say I take an empty cup and I take an ice cube and I put the ice cube in that cup. Suppose that cup's at room temperature at, say, 70 degrees. Well, what's going to happen? That ice cube is going to melt. It's going to turn to water, and then it's going to become, that water will take the shape of whatever the cup is. And so you ask yourself then, how can, and this is something we'd like you to be able to do, especially by the end of the semester, what is that process of ice becoming water, taking the shape? Was that ice always a fluid, or was it a solid? So these are cool things to think about And as we go on, you might ask, how can you explain them given the information that you read about, that we talk about, the problems we solve, all that kind of stuff. So okay, so there's two ways to study fluids, and not two ways, but there's two sort of main branches of fluids. So what we're going to do is we begin with fluids that don't move. Such as water in a cup. So we just have a cup filled with water. It's not moving. It's not like water running through a hose, or, you know, salt water coming out of a syringe, or, and, you know, an IV going into a patient type thing. There's not fluid moving. We just have fluid at a standstill. Maybe you fill up your bathtub and you want to do some experiments. So the fancy word for this I don't want to say studying this. That's a silly way of saying it. Excuse me. So I always hated in that. I feel like in the morning I sound like I've smoked cigarettes for like the last 10 years. I don't even smoke cigarettes, but I feel like I sound like an old grandma who smokes. I don't know what I sound like on your end, but that's what it sounds like to me. All right, so what we call this is, we call this hydrostatics. That's the fancy word. So we can't just use the words, we're going to study fluids that aren't moving. We got to use this fancy word, hydrostatic. Hydro meaning fluidish, waterish, whatever. Static meaning not moving. And then later we'll talk about moving fluids, and we'll call that hydrodynamics, because it's dynamic, it's moving. Real fancy. So one of the more important things to study with fluids that are just standing still would be pressure. So that's where we're going to start. Again, if there's not, think of it this way too. What can you really investigate about a cup of water? Well, you might ask how much pressure is on the bottom of the cup. That could be important for more real world problems. Like if I had a dam, I need to figure out how to build my dam so that it doesn't break. Or if I'm building an in-ground swimming pool or an above ground swimming pool, how do I strengthen the base and the side? So one of the more interesting things we can study with a non-moving fluid is pressure. So some questions you might think of, like, you know, if you go scuba diving and you're, you know, imagine, you might argue that the water's moving, but let's pretend that you're in an ocean and, you know, you're 30 feet below the surface of the ocean. You can, for all intents and purposes, assume the water's not really moving. You might ask yourself, okay, what pressure is that water pushing down on me? Will my lungs collapse from too much pressure? How do I explain why when I'm in a swimming pool that's 3 feet deep and I go to the bottom, I don't feel the same sensation than if I go 12 feet deep in the water? Okay. So Does anybody have any questions actually before we begin? I don't know. I should have asked that sooner. I don't think anybody's chirping. Who knows? You guys might all be sleeping. I don't even know.
No.
So, here's the problem. How much pressure does the water put on the bottom of the cup? So this is a very simple exercise, and it's a very simplified version of a much bigger problem, like I suggested. Scuba divers or something deep at the bottom, you know, maybe you have to put something at the bottom of a swimming pool for a cleaning device, or maybe in the bottom of a sewer system we have to put a door. How do we know how much pressure the water is putting on something? How do we know how long it will last against certain pressure? So we want to be able to answer this. So in order to sort of formulate and solve this, we need to simplify the problem. So I'm going to call this a cylindrical cup. And I'm going to draw a picture to sort of make it clear. So here's my cup. I guess I should have drawn it a different color, but we'll change this for our water. We'll use a light blue. So we have a cylindrical cup. We want to know how much pressure is on the bottom of that cup. So what do we need to recall? We need to recall the definition of pressure. That's force divided by area. Now we need to ask ourselves, what forces are involved here? If the water's not moving, if it's just sitting still, then the only force involved is we have gravity, at least we think, acting on this water. So it's making this water, which has a mass, the mass times the gravity equals the weight of the water. So that is the force. So we need to make that clear. So what's the weight? Weight equals mass times gravity. So we have two important equations here that we're going to somehow try to manipulate. The first one is the definition of pressure. And the second one is the force due to gravity, which we call weight. Now, a common question we might have is we might say, okay, well, hold on, O'Grady, if that water is a fluid, isn't the air above it in the cup of fluid? And isn't that also acting on this, right? And if I say no, then if one of you are sort of witty enough, you'll say, then why the hell do we care about things like atmospheric pressure? Clearly that matters. And it is going to matter, but let's assume for a second that we're only worried about the weight of the water. And then we'll get to the more general situation in a second. All right. So what we need to do now is we need to do a little bit of algebra. So bear with us. So let's call this guy star. And we'll call this guy square. So we're going to plug star into square. And so what happens is you get P equals, instead of force over area, I get W over area. Which is mass times gravity over area. Now, that doesn't look very useful, and it turns out that we're going to be able to rewrite it in a more useful manner in a second, but we have to think about some things that maybe we haven't thought of maybe ever. So one word we haven't really used yet that turns out to be important is what's called density. So if we think of it this way, what we want to do is we want to say, is there a cleaner way of doing this? And when I mean cleaner, look at this formula. Sure, we can compute it. But what this formula doesn't have is it doesn't have something that should be an obvious thing that we realize intuitively affects the pressure. So earlier I referenced this thing where I said, if you go in a swimming pool and it's 3 feet deep and you go sit on the bottom for 5 seconds, you might not really notice any sensation in your ears or your head. But if you went to the local community pool that's 12 feet deep and you swam to the bottom and sat there for 5 seconds, you're going to notice a different sensation. And what we all intuitively know, and at least we imagine this if we haven't experienced it ourselves, is that the deeper the water, the more water there is, the more pressure that we're going to experience. And so that also tells us that the more water that's in this cup, the more pressure it's going to put on the bottom of the cup. I mean, that just seems logical. Right? Now, the problem with these equations I have on the screen right now is they don't obviously show us that. We don't see anywhere where the depth of the water is in play. Nowhere in that equation do you see how deep the water is, because it's hidden right now, and we want to bring it out. So what we need is we need to somehow find where the depth of that water is hidden, and I don't want to say extrapolate, that's too fancy of a word, and figure out a way to rewrite mg over a so that we see the depth. Because then we'll have a very clear relationship that also matches what our mind tells us. So let me make that a point right here. Someone have a question? Or someone, okay. You're allowed to talk. I don't mean to say you can't talk. Sometimes I don't know if I can hear you guys or not. All right, so let me say this again. We want this expression to show depth. So what I want to do is I want to figure out a way to do that. So on the next page, that's what I'm going to do. So again, I know I haven't explicitly defined it yet, but it's a very important term. And it's going to be something we study, excuse me, or we use the rest of the semester. Okay, so what is density? So that's what we need. We need density. So what is density by definition? What it is it's mass per unit volume. So what we use is we usually use the Greek letter rho. So for those of you unfamiliar with this, it kind of looks like a slanted or a drunk P, but it's called rho. Spelled R-H-O, but it's pronounced rho. And so this is the magical ingredient. Because what's nice about rho is we can write it. So we can take this guy and you can rewrite it by, when you were children in school, they called this cross multiplying. But if I take this, I can write mass as rho times volume. So what density does is density allows us to get the size of our fluid involved. We didn't see the size involved before. Now we do. And being that we have a cylinder in particular, or any three-dimensional object, remember that the volume of a cylinder is its area times its height. So now what we've done is we've now got our height involved. Our height is now involved, our depth of our water. So let me go back a page and explain that again. We started with pressure. That's what we wanted to learn. And we assume that currently the only force acting on our water is its weight, or gravity, I guess is the better way of saying that, which is the weight of the water. And so when we write that in, we get that pressure is the mass times gravity over the cross-sectional area of the base. And that's not a wrong formula. It's just not as descriptive as we can be. We can be more descriptive. And so what I'm going to do is I'm going to take this M right here, and I am going to replace it with this M. So here's what we have. So if we go back to P, pressure, is mass times gravity over area. But if we plug this in, we get rho times area times height times gravity all over area. And then, as children, you learned that if I had a rational expression, if I had a fraction and the numerator had a common factor in the denominator, I could cancel them. The area cancels out. We're back to like 7th, 8th, 9th grade math here. And what you're left with is a very descriptive formula, which I'll summarize right here. And I don't know, let's pick a color. How about this? I don't like that color. We'll use purple. So we'll put it in this little cloud of awesomeness. Pressure is rho times height times gravity. Now, why is this much better formula for us? Because it is completely the formula that has the pieces that we know our intuition would have. If we've ever sat on the bottom of swimming pools that are different depths, we know that the depth of the water is playing a role. This equation is explicitly showing us that. It's telling us the two. I mean, I guess we can just sort of ignore gravity for a second. We all know it's there. We don't really think about it. But you can imagine now the density. This is telling you that density is completely determined on how deep the water is and how dense the fluid is. Whether it's salt water or regular water, maybe it's some other fluid like mercury or something. And look, what's beautiful about this, and this should not be forgotten. I use the example of water in a cup to derive this formula. Because water in a cylindrical cup, I can derive this formula just using algebraic manipulations. That's what we did. But this formula is valid in many more general situations. It's just to derive it would have required, as I said before, other types of math, calculus type stuff. But this formula is valid, not just for a cup, not just for a beaker sitting on the table of a chemistry lab, but it's valid for any container holding a liquid. It's valid for a turtle walking on the bottom of a river. It's valid for you scuba diving in the ocean. All right. So that is the very simple case. Now, this is not complete. As I mentioned earlier, you guys, if you're being sort of using your brain, you're like, oh, boy, we know there's more to it than this, because we know that, for instance, if I'm at sea level, pressure is different than if I'm in Denver. And so we know that the atmospheric pressure is also going to play a role here too. Okay, before we get to that, does anybody have a question now? What a time to be alive. Nice little Wednesday morning. Drinking my chemicals. My nose got sunburned yesterday. Can you believe it? Damn sun. This sucks. We can't, if we're in a real classroom, we can ask you real life questions about who believes in sunscreen, who believes in the Roni, and will Wolf free us today? Will he not? Can we insult certain politicians? Can we defend others? This would be so much fun to do in real life, but we can't. And I can't say anything on here because you might take my jokes as seriousness and turn me into an authority or something.
What's the difference between doing it online and doing it?
I don't know. I just don't feel comfortable. It's like text messaging. Context is key. You never know, right?
Sure.
Context is key. You might not get like a gesture I make that could tell, like throw my hand. Like, I don't know. It's fun. These are, we'll have it on the test. We'll insult everybody. We'll have one problem, we'll insult the president. The next problem, we'll insult one of the snowflakes leaders, and then we'll just, if you insult everybody, then everybody it's just as fun, right? All right. Anyhow, see, you don't know. It could have sounded like I said assault, and that would be bad, but I said insult. See, there's two different things. Okay, so what we've really just done, to be fair, is we have determined the pressure the water puts on the bottom of the cup, or the pressure the water puts on the bottom of the ocean. So nonetheless, this is a very useful formula. It will pop up many times, and it's part of the bigger picture. So to complete the problem, we must also consider the atmosphere's pressure. So if we draw our cup again as our little model to explain this, let's put our little water in here. My 7th grade art teacher, Mr. Bonga, would be so thrilled by my ability to sketch water in a cup. So what do we have? We really have two forces happening here. So we have a force here, which we'll call maybe the top force. I think that's what the book uses, so we'll go with that. And then we have a force from the water, which I think they call the bottom force. So if, again, let's be very clear what I'm sort of saying here. This is coming from the atmosphere. And this is coming from the liquid, water, whatever it is, fluid. I shouldn't use liquid. We called it a fluid. Say what you mean what you say, I guess is the way. Okay, so I'm going to spare you the algebra this time, but I would encourage you to go through it. It's very similar to what we did in the previous problem. So I'm not going to say you should, but I'm going to say you might want. So what does the algebra give us? It gives us what we assume. I mean, this is not rocket science here. It gives us that the pressure on the bottom is equal to the pressure from the top plus what we found before, which is rho GH. So basically, I mean, this is almost so much rocket science, we don't know what to do with ourselves. But as you would imagine, if you have a liquid sitting in a cup, the total pressure on the bottom of that cup would be the pressure from the water plus whatever the pressure is pushing down on that water. I mean, this is, I don't mean to sound like a jerk, but that's what this is saying, right? And so, again, if we trust that this is true not just for a cup of water, but it's true in general, you get a very sort of obvious situation In that situation is that if I have, basically we're saying pressure is additive. That's it. So in general, what this is saying is saying the following. So as our intuition suggests, the fancy math word for this is additive, but it just means the following. So if I have two pressures, P1 and P2, the total pressure is the sum of the two pressures. That's what we're saying. And your intuition suggests this anyhow. Does anybody have a comment or a question? So problems like this are pretty simple. I can say you have a cup of water on a table and the volume is blah or the depth is blah. Calculate the pressure. I mean, these are just plug and chug problems. They're not very enlightening. But at that point being said, these simpler problems will become more involved once we sort of change the scenario a little bit. All right, so what's next then? Well, we now want to look at sort of the next step in the intuition. What happens when we submerge objects into a liquid or a fluid? So what happens when an object is submerged in a fluid? So you guys, if you've ever been in a swimming pool or a bathtub, you know that there are a few options here. For example, what happens to you when you jump in a body of water? Do you float? Do you sink to the bottom? Do you sort of go 3 feet under and just stay there in the same place? And so we want to describe the physics of this, or at least quantify when it does one of the three things. So I hope everybody understands this sort of question. So these are the options that we have. Now, again, the analysis that we're going to do is going to be on a simplified quote unquote model. We'll use simple shapes that have simple geometry, but these formulas are valid in most settings. It's just the derivation is quite complicated. So probably the best way to sort of answer this question in a specific case is to do the following. So here's our simplified model. So a cube has how many sides? A cube has 6 sides. So we would imagine that if we submerge our cube in a fluid, there's going to be 6 forces acting on it. So let's sort of think of if we can draw this. Now, so if I draw my cube, oh, Mr. Bonga would be impressed. That's a pretty damn good cube. And so we got to now do this little dotted line business to show perspective. So let's think about the forces we have. I'm going to use certain colors to try to make this useful. We have some force coming down, which I'll call force 1. And then I'm going to have another force pushing up against the cube. We'll call that force sub 2. And then we'll get another color here. Let's get, how about purple? So I have a force coming against this particular side. I have a force coming against this particular side. And then, of course, I can't draw. It's going to be too hard for me to draw, but you would imagine that say the front and back, there's also forces. So I guess maybe I can try to do that. We'll use pink. Maybe we try to say that there's a force coming. So we'll draw it this way. F5 against the front. And then F sub 6 against the back. Hopefully that makes sense. I don't know, maybe it does, maybe it doesn't. Now, we're going to assume some things like that you might not even think to assume, but assume the density of the fluid is uniform. And then if we think about Newton's laws, for example, one of Newton's laws says every action has an equal and opposite reaction. And so what these forces, for example, force 3 and force 4, everything that force 3 does, force 4 cancels out, right? They're opposite. So the fancy word for that is what they're called normal forces. So what you need to understand is F3 and F4 cancel out. And then F5 and F6 also cancel out. And again, a good way for you to think about this in the real world is if you were to take some object and you're standing in a swimming pool and push it down, as long as you push it straight down and let go in a very uniform way or it's not going to shoot left or right. It's going to shoot either straight up or it's going to sink straight down. Of course, if the water's not moving, if it's under a controlled environment. What we're saying is those forces on the left and right aren't doing anything under ideal conditions. The forces on the front and back aren't doing anything. The only thing we have to gauge is the force pushing up stronger, if you will, than the force pushing down, and vice versa. Because that's going to determine whether we sink or whether we rise up and float. And if F1 and F2 are the same, which depending on certain things, it could be possible, then the object will just stay exactly where you let it go. So I keep using swimming pools as an example because I've been spending time in there lately, and I have a 5-year-old who jumps in the pool and puts things in it. But it's, you know, oh, I see, this is what my weird ass mind thinks about. I'm thinking about the physics and the math of everything. But it's also, most of us, I shouldn't do these assumptions. Maybe some of you are like, I've never had a pool. Screw you, O'Grady. I think most of us at one point or another have jumped in a pool and done these things. Okay, so again, the only forces that will, under ideal conditions of us not moving the water or of us not pushing it down this way or that way, if we just do things under controlled conditions, the only thing that's going to matter is what's pushing down and what's pushing back up. Now, we would assume that F2 is bigger than F1. And the reason for that is that the water depth, or I keep saying water, but you can imagine water, but the fluid's depth is bigger. All right, so what we want to do now is we want to look at a similar analysis to what we did before. Let's look at pressures now. We're going to say pressures. So that's what we got to do on the next page. All right. So it remains to consider only, you leave, oh, hold on one second. Where are you going to the, hold on, peeps. I got to say goodbye to my crumb. My kid has a doctor's appointment. She's like, she goes yesterday, do you get shots at checkups? I said, I don't know. I hope she don't get a shot today. Shots, they terrify these kids. You never know why. All right. So what we need to consider is we need to consider F1, F2, and then, of course, P1 and P sub 2. So I hope you guys understand that when I say P sub 1, we're using these subscripts so that we can easily say that P sub 1 is associated with F1 and P sub 2 is the pressure associated with F sub 2. So again, it's hard. This is probably one of the biggest faults of someone who would teach a class like this, is we always forget that you guys, you know, subscripts are so common in math and physics and in science in general, and we're so used to using them, we often forget you guys probably haven't used subscripts in quite some time. So I'm going to do my best to try to always remind you what's happening here. Okay. So what can we say? Again, don't forget, I'm going to put it on the right-hand side because I remember, that we often forget this. In general, pressure is force over area. So another way of writing that is that force is pressure times area, right? If I just write the equation differently, multiply both sides by A. So what does that tell us then about what we have? Well, if we consider the top force, we know force coming from the top, force 1 is pressure, P sub 1, times the area. I guess I don't need these dots for multiplication. Whether you, I think you guys, I hope that when you see me write a letter followed by another letter, that always means multiplication. I hope we get that at this point. Now, if we draw our cube for a second, let's sort of, let's draw a picture over here so that but I'm not going to draw it in 3 dimensions because it's going to be too hard to make a point here. If this is my cube and it's submerged in some liquid, and I'll sort of think of it this way. So what we'd like to do is we need to give sort of dimensions to my cube. So if I say my cube has 6 sides, here's another picture of my cube. What are my dimensions? Well, I have to give it a name. So why don't we call it L, 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 right? Let's say every side is length L, L for length. So if we agree that that's going to be the case, then the force 1 becomes pressure sub 1, and then this is the area of the top is L times L. So this is L squared. So if we write it in this more descriptive way, we get F1 is related to P sub 1 in this way. It's good to take a moment and pause and think about numeracy things here. Go back to like your heyday in 5th grade, 6th grade. And people my age and younger, like, so you guys most likely fall into this category. One of the things we missed out on, because it's sort of like an unintended consequence of technology. I grew up with calculators, and so I'm assuming you guys did use calculators in math class as well. But what we lose out on is when we're using calculators all the time is we lose out on these sort of numeracy skills, these understanding how multiplication and how division and fractions can tell us things just by looking at a formula. For example, if I look at this equation, P equals F over A, I can make lots of very interesting sort of observations about how pressure works. You know, if I keep P and F fixed, but I make A bigger, if the area that the force is acting on is very big, then the pressure is very small. Whereas if the area I'm acting on is very small, then f over a small number, if you take f and take a number and divide it by a really small number, that's in essence the same as multiplying by a large number, and so the pressure gets big. And so if you a good experiment for you to make sense of that formula is the thing that you've probably done before, is you've all popped balloons before. What's easier to pop a balloon? Is it easy to pop a balloon by squeezing it? No, well, you can, but probably the easiest way to pop a balloon is to take a pin or take the point of a scissor and just tap it real quickly, because you only need a small amount of pressure on a small piece of area, and that's what that formula is telling us. So nonetheless, if we look at this formula now, f sub 1 equals p sub 1 L squared, once again, we get the obvious thing. The bigger our cube is, the larger we expect the force is. Because if L's big, then L squared is bigger, and that makes f sub 1 big. And then, what's the obvious, the corollary, or not corollary, but the analogous thing? What is f sub 2? F sub 2 is equal to p sub 2. L squared. Now, we also know, and this is important too, we talked about this before, we know that p sub 2 is equal to p sub 1 plus rho gh. So now we have three important formulas. But our height here now is different. What are we thinking about? The height here would be the difference between the top of the cube and the bottom. So what we can do is we can take this h and we can replace it with L. Whew. All right, now at this point, you know, my job is to try to pick and choose how much of the algebra to show you and how much to, as we say, leave to the reader. That would be you or the student. We're going to combine these things now, and then we're going to do some algebra. And again, why are we doing this? Well, what we'd like to do is we'd like to get a nice, concise formula that is explaining to us the situation as our intuition explains it. So before I do that, or before I skip steps and show you the actual stuff, remember, what was the question we posed? We posed, I put an object, this cube, I submerge it in water. I let it go in a very controlled way. What does it do? Does it stay there? Does it sink to the bottom? Or does it float up? Now, our intuition and our intelligence tells us, well, of course, it's going to depend on what kind of fluid it's in, and it's going to depend on what the density and what sort of forces we have. Okay. So here's what we want to do. So actually, let me go back because I want to make something clear. we have an expression for f sub 2. We have an expression for f sub 1. But again, as we said with the previous sort of problem, these expressions are completely valid, but how informative are they? Do they give us enough information that we can make sort of observations just looking at them? And the answer is right now we can't. So what we'd like to do is we would like to plug this pink guy, this pink expression for p sub 2 into this expression. So what I'm going to do is I'm going to plug this guy into this guy. So here's what I mean by that. We have f sub 2, and we know that it's p sub 2 L squared. But now I'm going to plug that thing in. What's p sub 2? P sub 2 is p sub 1 plus rho g L, and then that's L squared. And then I'm going to do some algebra. You will remember many years ago, you learned this thing that you've probably thus forgotten called the distributive law, where you can multiply and you get p sub 1 L squared plus rho g L cubed. Okay, now, here's what's going to be very, very, again, we're trying to come up with some sort of way of, I mean, I keep kind of repeating myself, and maybe this is not the best learning experience, but what I'm trying to get at is we can write down lots of different formulas that are correct. But the question is, how do we get a formula that's very descriptive off the bat? Well, it turns out this, even though it looks overwhelming, is very, very informative because we can do the following. Remember that the question we're trying to answer is I keep repeating myself, is what happens to our object? Does it go up? Does it go down? Whatever. And if we think about that experiment, we would imagine that what's going to decide that is the interaction of force 1 versus force 2. And so what better way to see how that war is going on than to take one and subtract it from the other? So before we do that, let's do the following. Since L3 equals volume, we can write as follows. We can write f sub 2 equals p sub 1 L2 plus rho g times volume. Remember, what's the volume of a cube? It's length times width times height. And since all three are L, we get L cubed. Now, why am I going to put it back in V? Well, don't forget, the formula we're going to end up with is not just restricted to a cube. We're deriving it with a cube because the geometry is easy, but turns out it works for any type of object as long as it's geometrically sound. So this is important. So now let's compute f sub 2 minus f sub 1. What is that equal to? Well, that is equal to, if you remember, F sub 1 is just P sub 1 L squared. So right here, this is actually F sub 1. This is just F sub 1. So if I subtract that out, all that's left is this rho GV. So what we just did is we in a long-winded way, we did some geometric assumptions, assumed simple geometric figures, and we showed that F sub 2 minus F sub 1 is nothing more than rho, that's density of the fluid, times gravity, times the volume. So, the first thing you'll note is that rho is positive, G is positive, and V is positive. If you pick one convention where gravity, we're thinking of it as a positive number. More importantly, we would imagine then that the density of the fluid and the volume of the object would have everything to say about whether we float or not. And so this term, this difference becomes very important, and we give it a name. So we define what's called the buoyant force. F sub B, and it's equal to rho GV. So this is the sort of formula that is going to tell us when something floats or sinks. Now, what's interesting is humans have known about this, sort of, maybe not the algebra of this, but they've understood the intuition of buoyancy since the days of, as far back as written history goes. Archimedes was one of the first people who's credited with figuring out when things float. And we have the following awesome principle due to Archimedes, and so we'll so and I'm going to be careful with my words because, well, I guess that doesn't have to. So an object submerged, and it can be partially or fully, in a fluid feels a buoyant force equal to the weight of the displaced water or displaced fluid. So this is an interesting principle, and I think I'm correct in this. I'd have to double check, but we could do that another time. But I'm pretty sure that this kind of stuff was discovered. I mean, this was one of the original ways that humans figured out how to measure the size of objects. If you wanted to know the volume of an object, in general, that's a very difficult problem to solve. It requires calculus. So imagine 2,000 years ago, they didn't have calculus. So how did we determine the volume or the size of different objects? What you do, you'd place them in a fluid and you would measure how much of the fluid was displaced. And then that was one way of determining the size of an object. And along the way, of course, if you're submerging things in fluids and some things float and others don't, you become curious, well, why the heck does that happen? And so here you go. Okay, so here's an interesting way to sort of quantify this and use it to answer questions. So we can now define what we call apparent weight. So what is your apparent weight? Well, it's your true weight minus the buoyant force. I think this is the notation your book uses. I'm trying to stick with the book. Hopefully you're reading the book. And I'm pretty sure they use these subscripts where they spell it out. So what happens if you work with this formula, what you'll realize is, and we'll maybe let you ponder that until next week. One of the things you'll realize if you work with this formula, if you think about the algebraic things happening here, it turns out, and this is really cool, what really matters in all of this, as you would have guessed initially anyhow, is what is going to determine whether something sinks or not. What's going to determine whether it sinks or not is going to be if you take the density of the object and compare it to the density of the actual fluid that it's in. So anyhow, maybe we'll leave that for another time. Probably the best thing to do here is let's pause and then not pause, but stop for today. We'll post some homework, you work on it, and then when you have questions, you ask. Does anybody have any questions or comments? Concerns about life, this class? Anything? Good, because no, I'm just kidding. All right, then. Well, then I will stop this now. If you have questions, feel free to ask or send me an email. If I don't hear from you, have a good weekend. Hopefully, we'll see you guys Monday.